Welcome to A Conversation with History. I'm Harry Chrysler of the Institute of International Studies. Our distinguished guest today is Jim Peebles, who is one of the world's foremost cosmologists and emeritus professor at Princeton University, where since 1984 he was the Albert Einstein Professor of Science. Professor Peebles is the Hitchcock Professor on the Berkeley campus for the fall 2006 semester. Jim, welcome to Berkeley.
Thank you.
Where were you born and raised?
In Manitoba, the center of Canada, to the south of the province, born in early life in St. Boniface, the sister city of Winnipeg, then later in St. Vital, public schools, small schools, and then on to the University of Manitoba.
And looking back, how do you think your parents shaped your thinking about the world, or maybe in your case, I should say the universe?
We didn't talk about the universe. My father, though, was very good with his hands. He built things, and that very much grabbed my attention. I, as a youth, didn't pay too much attention to the stars, although I remember being impressed by aurora, but I did pay a lot of attention to building things. I'd build sleds, I'd build inexpensive radio receivers. I like to work with my hands, and that, I think, must have been inspired by my father.
As a young person, were you drawn to science? I mean, in high school, middle school?
I didn't know what science was in high school. It wasn't I shouldn't complain. It was a good school. I learned things, but I didn't learn very much about modern science, even modern mathematics. It was quite a shock to go to university.
And you mentioned your university. In what way were you shocked, and what did you major in after the shock?
It was a wonderful place. So many bright people doing so many interesting things. Because I was not a diligent student in high school, I didn't have a clear idea what I wanted to do, except that I did feel I'd like to continue with education. I knew I liked to build things, so I enrolled at the university in engineering. That was okay, and I guess I could have become a mediocre engineer, but to my great good fortune, friends persuaded me to transfer over to physics. I can't say it was a eureka moment. I just stopped complaining and started doing my homework.
So it felt natural to you?
Somehow it felt right.
Yeah.
And I never looked back. I never had asked myself, should I have done something else? No, this was right for me.
Did you have any teachers at the university that were very influential in pointing you in a particular... Super. It's not a world-famous university, perhaps, but there were excellent faculty, and they really inspired me in physics. I consider myself a physicist, not an astronomer. And I took no courses in astronomy. I didn't even know about stars when I left Manitoba. And then where did you go to graduate school?
Princeton University in New Jersey. I came there intending to continue my interest in quantum physics, particle physics, but didn't, although there were excellent people doing that sort of thing at Princeton. Instead, I met my lifelong teacher from then on, Bob Dickey, who inspired me to follow him. He had been a great contributor to quantum optics in the years from the Second World War into the 50s. He was one of the leading figures in figuring out quantum optics, the development of masers and lasers, some wonderfully ingenious inventions in that field. But then he decided gravity physics was being very neglected as a subject for research in physics. He started working on that, and what he was doing was so fascinating, I just trailed along.
And what did you wind up doing your dissertation on, I assume under his influence? Under his influence,
project of, there is in physics constants of nature, the numbers that characterize interactions. In particular, the strength of the electromagnetic interaction is measured by a number, we call it the fine structure constant. Bob was fascinated by the question, could such numbers be not fixed numbers, but rather vary? It was, on his part, more philosophical than based on anything firm. Somewhat ironic that these days, within superstring theory, people are convinced these numbers ought to vary with time and maybe slightly with position. In any case, he set me the task, find evidence that would constrain how much this number could have varied through time. Turns out there are lots of ways to do it. In particular, in those days, one had pretty well developed already the concept of radioactive decay of long-lived isotopes as a method of measuring the ages of rocks. Different radioactivities decay at different rates, leave different products. You can count the products, deduce an age under the assumption that the decay rate is constant. But if the strength of the electromagnetic interaction were varying, that would change the decay rate, and so different decay chains would give inconsistent answers. Kind of neat. So I learned some geology, which I'd never done before. And I learned some astronomy, because you can also look at great distances. You see things as they were in the past, and again, make some checks. So my thesis, in a way, was leading up to some very modern ideas. I had no idea, of course.
I get the sense in your lecture and what you're saying now that this community that you're a part of, and it may actually transcend the particular subfield within physics. It may include all of the sciences, that there's a kind of movement forward as the kind of collaborations emerge or the insights emerge, which then influence your own thinking. You just suggested that in your dissertation.
Oh, yes, yes. We build upon previous work. It's so important that we have a basis of knowledge and understanding that we build upon, and we hope add to, for the next generation. By no means is any one individual. One of my heroes is Bob Dickey, my teacher. But I have to admit, he wasn't essential to the game. Others would have done what he did. What is essential is that institutional memory. I sometimes think of science as a craft, in the sense that you learn it from the previous generation, who learned it from their previous generation. I would hate to imagine doing science de nouveau. To start all over again would be to start all over again. We'd have to go through another Galileo, another Newton.
This touches on a question that I always like to ask the scientists, that is, what are the skills that people should have? And also, what are the virtues that make for a good scientist?
In part, what's the most optimum skill is a function of time. As the subject evolves, different skills are needed. I have the strong feeling, for example, that another respected figure, Fritz Zwicky, was just right for his time in astronomy, when there were lots of new ideas poorly explored, but might not have done so well today when we have a fixed set of ideas that we're trying to build upon. He was too independent-minded in a way. It's good to be independent, of course, but you have also to pay attention to what other people are thinking. He didn't like doing that. That was right for his time, now it's not. But of course there are surely general features that people should carry along, and one of them, intellectual honesty. Did I really say that? You may ask yourself, oh, what a stupid thing to do. In life, it's very difficult to say that sometimes, but if you're going to do well in science, you'd better learn from your mistakes. So that is one, I think, introspection. Ask yourself, did I really mean that? And is this observation really consistent with my fixed beliefs? Of course, there are many kinds of science, too. There is the deeply mathematical sort, like superstring theory. Those guys can't pay too much attention to the data because there isn't much that's relevant to their deep ideas. On the other hand, the kind of science I love doing is that which comes into pretty close contact with what people are measuring. And there I see a lovely interplay. What are the observations suggesting? What does the theory suggest? Are they really consistent? Curiosity, of course, in any human endeavor, surely. An interest in what's going on. Mathematics? I have never been a very good mathematician. I struggle with it. I hate it.
Must be speaking, relatively speaking.
I don't know, but it is true, I think, that I only do mathematics because it is it produces this wonderful interaction between theory and observation. I think if that weren't happening, I would do something less difficult. What would it be? I don't know.
A theme, well, go ahead. Did you want to add anything else? Because I was just going to...
No, let's go on.
Well, one of the themes that emerged in your lectures, and often in my discussion with scientists, is a willingness to collaborate but also compete, basically.
Oh, yes. Oh, yes. We're a nasty bunch. We try to get ahead of the other person. That's partly, I guess, just human instinct, isn't it? You like to run faster than that friend next to you when you're jogging. Competition. It's not unhealthy. But cooperation, we'll get nowhere without it. And so, yes, I have to admit, you have the better argument there, but I'm going to get you next time. Competition, very important, though. Why? As I reach the golden years, I feel less competitive, but I still want to beat out that other person. That's
good. Let me see if there was something else. Yeah, I did want to emphasize, again, something you just said, but you said it in the lecture, this synergy between theory and observations. That is, you know, it's really an important part of this work that you're doing. It
is so important. Of course, this is what science is, in my way of thinking, the synergy. It's been there since the beginning. When we run out of synergy, then science goes in a very different direction, and one that I'm not sure I want to follow. There was never any guarantee, you know, that this synergy would be useful. No one ever guaranteed that we'd be able to make sense of the world around us. It's a striking thing that we've come as far as we have, and we've come an amazingly long way. All of modern technology, so much depends on that curiosity-driven research, the synergy of a decade ago, a century ago. Will it continue? We'll find out.
You were talking yesterday in your introduction, the second lecture, and you were talking about what science is, and you said science as a search for successive approximations. Good approximation to reality, but a long way to go. No absolute truth in the physical sciences. So in a way, you have to live with uncertainty and frustration, I guess, if you're going to live by that ethos.
Oh, yes. You know, there is talk of the theory of everything. I think it's poorly chosen words. They don't really mean that. No one in physical science fools themselves into thinking we know absolute truth. Always, we have to accept that although we have brilliant successes, we also have amazing gaps in our understanding. The gaps are being filled, and it is characteristic of our subject so far that as you fill gaps, you open new ones, new questions arise. I wanted to emphasize that because one misconception about science often is that, look, if you can't answer all my questions, then you don't know what you're talking about. But that isn't true in science. We can answer some questions very well, and we can prove it by the technology to which these answers bring us. But at the same time, there are open issues. And of course, if there weren't those open issues, there would be no more science to do. And we're not in any danger of being in that state.
Now, this relates, I think, to a problem that science probably has in its broader environment, that is the field, which is the really key here is doing basic science is very important, because there the people who fund the science, whether it's the government or the foundations, whatever, can say, well, what's this for? You know, why should we do? So that is a really key element. So this uncertainty, as one looks for these approximations to move toward truth, is also enveloped in big questions whose relevance might not be clear to people who are not doing the work.
And we must emphasize the excitement, the adventure of exploring new questions and, on occasion, finding answers. That excitement, I believe, carries on to excitement in more applied areas of physical science. I've got to hope that an engineer who develops the next generation of cell phones they should only make them not work in automobiles, will be in part excited by what the engineer sees around herself of advances in other fields, including the most basic. I would never claim, maybe I'll be wrong someday, I'd never claim that my subject is going to be of any practical use. Who cares what's going on in that distant galaxy? Except that you really do care. Isn't it neat to think that you can deduce properties of a galaxy way over on the other side of the observable universe? Neat to think that we can understand its nature in broad outline, even though we'll never be able to go over there and poke our finger on a planet in that galaxy and ask who's home. Intellectual excitement, I hope, is an essential part of our society and of its growth.
You're touching on something, because people who don't do physics are really interested in the stars. They're stargazers. I mean, of course, there's all of, at one level, we know the interest in science fiction, and what's, beyond what we can see with the naked eye and so on. And then, of course, it gets into a moral dimension. Who are we? What is man? How were we placed here, and so on. So any thoughts about how physics can lead to a place where other people are posing questions, although they have no interest in the physical science?
A remark about physics and astronomy. Many people are fascinated by astronomy. It's astronomy's secret weapon. Surely congressional aides are a little bit biased toward astronomy. I am now, what am I called? I am now a naturalized citizen. I was for many years a landed immigrant. I actually had a green card that was green, that old. And in those days, when arriving from a trip overseas, I would have to explain to Customs and Immigration what I did for a living. And I would sometimes say, I'm an astronomer. Oh, isn't that interesting? Or I might say, I'm a physicist.
Yeah.
I took physics in school and I hated it. You notice that there are amateur astronomy clubs. These people are marvelous. They work all day at a job, and then at night they do what they love, astronomy. I'm so embarrassed. I do what I love during the day. I know of no amateur physics club. Amateur particle physics. Wouldn't it be marvelous if there were such a club? But there aren't. So that's the way people are. To me, I don't really draw a distinction between astronomy and particle physics. And I don't see any moral aspect to it all either, to be blunt. It's all part of the world around us. The small, the big, they're both neat. But I wouldn't give precedent to one over the other, I think.
I wonder if you would compare the awe that you feel as a scientist as you come to understand these structures of the universe, to say the awe that somebody feels who just, emotionally appreciates what they say by just looking at the stars, so to speak.
Or looking at a giant redwood.
Yeah.
Is the awe any different?
Yeah, that's the question.
To me, no. There is the awe of realizing that we can make sense of the world around us. Sometimes when I look at our political situation, I don't have that awe. But when I look at what can be done in astronomy, I am awed. But when I look at what can be done with the subatomic nature of matter, I'm awed too. It's both neat. And so is a tree or a person. I've just been reading a wonderful history of the discovery of DNA. What an awesome set of work. Brilliant. And I'm awed by the structure of DNA.
Do you think, if you think about the future of science, we have to train the next generation, even at the lower grades. So there is a commitment to this doing of science to discover truth, that, you know, even in the very young grades, we have to develop the skills there so people can go to high school and then go to college and then, if they choose, go get a PhD. But on the other hand, you know, the political currents are really calling that into question, you know, around issues not directly related to what you do. I'm just curious, as a scientist, what your thoughts are about that. How do we build the legitimacy of science in those communities where it's become problematic?
I wish I could answer that. I'm sure that a lot of the development of a scientist takes place in public schools, in the lower grades. I have no idea how that's best done. Of course, so much of it depends on the home environment. I was so lucky, although I didn't learn much in the way of formal science until university, I was so lucky in having parents that allowed me to build things. I could make a mess in the backyard and they didn't care. I have taught all my life, but I must say I hold in awe those teachers in public schools for the much deeper challenge they have. After all, when I teach, I'm talking to the choir. If the class is a little unruly, I lower my voice, and they all settle down. It's just so different. But of course, once we've got these people in university, then indeed there are things that can be done and must be done to keep them on the track to doing great things. And one of the most important, certainly, is a little bit of support for interesting new research that will inspire them, perhaps to continue doing research after education, or perhaps to go into something different but apply their skills. Not very expensive as a fraction of the budget of this country to keep research going. It's being squeezed these days. For small groups, the National Science Foundation is a major source of support. It is being terribly squeezed, so that many scientists who are doing small science, but that's the backbone, the small science groups that are teaching small groups of students to go out and do wonderful new things, are being squeezed to the point that many are closing down. The National Science Foundation is running out of money for small groups that are at the very basis for education.
I would like to change directions now and have you help me make our audience understand. Maybe they already do, but let's start from the beginning. You are a cosmologist. What is it that this field of the physical sciences studies?
The easy answer is the universe, but of course it's also the wrong answer. The universe is everything. I don't study you.
Right.
So when I say I'm studying, I'll try to work you in. But when I say I'm studying the universe, I really mean I'm studying what the universe looks like on the largest observable scale. It's a little surprising that I could make such a statement. How do I know there's a largest observable scale? To be a little more explicit then, I should say we observe that matter is arranged in a sort of hierarchy of structures. You and I are a little concentration of material here in the sprawl of the Bay Area on the planet Earth that's in the solar system, that's in a galaxy of stars, that's in a supercluster of stars, and so on. Layer upon layer of structure. It's kind of a neat arrangement. And of course it goes down in size too. But what is striking is that as you look on successively larger scales, you reach a point where there is no more structure. The distribution of material objects becomes uniform. No center that we can see, no edge. It's that wonderfully simple arrangement that is the basis for what we study when we're studying the large-scale structure of the universe. What is the nature of that large-scale distribution and what is its behavior? It's been speculated for a long time, fairly recently demonstrated, that this uniform distribution is nearly uniformly expanding. It contains fossils from the early universe, in particular thermal radiation. The radiation is cooling. It is observed that distant galaxies look younger. And that makes sense because we're seeing them as they were in the past because of the limited light travel time. We're seeing evolution. We're seeing the growth of departures from this large-scale uniformity. Matter is growing together in clumps, and the clumps are growing together in clumps of clumps. We are studying the growth of the big levels in this hierarchy of structure.
And is the concern only peripherally how it all started?
Oh, of course, you'd love to answer that question. You make it peripheral if you can't give it a good answer. And it's debated whether we have a good answer. To me, as an old-fashioned theory and observation type guy, we don't have yet a definitive answer. We have some very good ideas that people are working hard on, and remarkably enough, they're developing tests, perhaps clues to what was the universe doing before it was expanding. That's the next great generation of experiments in this subject. There are ideas, as I said, about what the universe was doing before it was expanding. They go under the name of inflation. Inflation is not a theory because there are so many options within it, so many hypotheses to be made and considered. So far we don't have any firm, we have very few firm predictions out of inflation. And unfortunately, most of these predictions were, in effect, post-dictions, the theory constructed to fit ideas that are now confirmed. But that could change. Things will show up. Search for gravitational waves that would have been generated by processes thought to have happened during inflation. Gravity wave detectors are being designed, and not only will they see interesting things produced in the universe as it is now, maybe they'll see some fossils from the universe when it was not describable by an expanding world model.
In your lecture yesterday, you talked about certain things that we know. I want to be sure to use the right term, but laws or principles, the uniformity, no center, no edge. I mean, these were the ideas that have motivated the research and have been proved in a way.
Yes.
You just mentioned that the universe is expanding but not evolving. Yep.
But evolving.
And evolving. Yeah. And evolving. Sorry.
Yeah, that's key. You know, there was a steady state model. I like it as an example of an elegant idea that has been ruled out. We often, you know, in formulating ideas about how the universe around us, the world around us may be operating, we do rely on our notions of elegance. But of course, our notions of elegance are really strongly informed by what works. But the steady state cosmology is an example of an elegant idea that was very influential, drove a lot of research, in part because it so infuriated some people, advanced the subject, but then was shown to be totally wrong. So goodbye, elegant idea. Let's look for another elegant idea. I interrupted you a bit there. You were... Well,
I know, but I'm glad, but what I guess what I wanted to help talk a little about some of the concepts that have emerged. In your lecture, you were talking about thermal radiation, dark matter, dark energy, and in your lecture, you really conveyed the sense of how our understanding of these terms emerged over time through generations as scientists had an idea which was either confirmed or disconfirmed by satellite observation. So give us a feel for that so people can have a little taste of that lecture.
Okay, let us choose an example. Well, first let's notice that you and I are made of atoms. They go under the general name of baryonic, bary being heavy. Well, historical term. We are made of material that is to us visible. The striking evidence that we have from studying the property of the universe in the large is that you and I and baryons in general make up only 5% or so of the mass of the universe. A little shocking, but we'll have to live with it. Pretty convincing evidence that there is dark matter that is not baryonic and whose properties are really mysterious. that there must be such stuff was known already in the 1930s. I mentioned Fritz Zwicky, one of my heroes. He was the first to point out that we have a puzzle. There's matter, there's mass out there that is not baryonic. There are great searches going on, including one beautiful project headed up here in Berkeley by Bernard Sadolet, looking for this dark matter through laboratory searches. Brilliant stuff. Then, fascinating to me particularly is the third major component of our universe, dark energy. The name is really meaningless. It was ad hoc, made up, but it fits with dark energy, dark matter. It had its origins already back in 1917 when Einstein had invented his new theory of gravity, general relativity, and found that when he applied it to the universe, it gave an absurd answer. The universe can't be stable. Of course the universe is forever. And so he adjusted his theory by postulating a new term that we now call dark energy. He called it the cosmic constant. It was a Belgian, Georges Lemaitre, in the late 1920s, early 1930s, who recognized that Einstein's cosmic constant acts like a zero level of energy. You know, in physics, energy is a quantity whose differences we care about, transactions, but we don't ever set a zero of energy. He became convinced that the zero level of energy is set by Einstein's cosmic constant. I showed in my lecture a fascinating exchange of letters between Lemaitre and Einstein just after the Second World War, in which Lemaitre tried to convince Einstein of the value of this concept. Einstein would have nothing of it. He grew to hate the cosmic constant because he didn't think it was needed. And if not needed, then away with it. To Einstein, simplicity is all. I did remark that other of the great scientists of that era, Wolfgang Pauli, brilliant person, would have nothing to do with lambda. Or Landau and Lifshitz, from the Soviet Union, a magnificent series of textbooks in theoretical physics. All of us learned so much from them. They would have nothing to do with lambda.
And lambda is...
Oh, sorry, lambda is dark energy. It is Lemaitre's dark energy. It is Einstein's cosmic constant. To these people, it was an ugly appendix. And they had a reason in part for thinking that, because we have the horrible problem in quantum physics that zero-point energy is real and important, and it's there, and it exists not only in material objects but in fields, such as the electromagnetic field. But a naive sum of the zero-point energy belonging to the electromagnetic field and other fields of nature gives you an absurd energy density with all of the properties of dark energy, Einstein's cosmic constant, except one, its numerical value is ridiculous. Forget about it. There must be something wrong with zero-point energy for fields. I know of nothing wrong with it. The argument is, I think, clean, except the answer is absurd. It's an illustration of how we have, on the one hand, a secure, well-tested theory, but on the other hand, it's only an approximation. There are holes to be filled by the next generation. Well, what is now charming is, on the one hand, people recognize there ought to be a zero of energy that would behave like Einstein's cosmic constant, Lemaitre's dark energy. It ought to exist. And through a series of experiments that began again in the 1930s by Edwin Hubble, who drove the development of a big telescope to make the measurements, the 200-inch telescope on Mount Palomar, by great scientists in the 60s when that telescope was at last finished, in particular Alan Sandage, driving forth the observations that might check for this dark energy. Then, just in our generation, here at Berkeley, Saul Perlmutter leading a group to carry on those efforts, and at last succeeding and showing us, of all things, that dark energy exists. The stuff that Einstein introduced, then discarded, that Lemaitre fought for, that many serious scientists discarded again, is there. What a neat story.
So, in a way, over time, not in the sense of the scale of time as one looks at the whole universe, but over time and over generations, there's this movement forward to come up with a concept that is confirmed. Now, in what sense in this process does the dark energy matter? I don't mean in terms of its utility for practical things, but relate that to this ongoing conversation of understanding the universe.
Yes, here it is. The dark energy exists. We should first pause to say that ideas don't always have the longevity of dark energy. Many ideas are thrown out and go away forever. But some curiously survive, often in a slightly different form. But now for us at this very moment, the key point is that we have the evidence for the existence of a new phenomenon that does not fit within our ideas of basic physics. Something's wrong, and we're going to have to remedy it.
And that's dark energy.
And that's dark energy. Its value is just wrong. Now, of course, there's no crisis here. There's opportunity, of course, but there are lots of ideas about how to remedy this. Down the road at Stanford, Lenny Susskind knows in his heart the solution to this problem. Others of us wonder, but that's part of the game, of course.
Now, in the introduction, in the program for your lecture, I'm going to read what it said, and then I want you to tell me what this means. It says, Peebles laid the foundation for many modern cosmological investigations by predicting the existence of cosmic background radiation, popularizing the notion of dark matter in the universe. What does that mean?
Well, it's, with all due respect, it isn't quite right.
Okay, let's correct the program right now.
This radiation, of course, was first understood before the Second World War by Richard Tolman at Caltech. After the war, my teacher, Bob Dickey, was the one who said, maybe there's this radiation, we ought to look for it. That was, at that time, he persuaded two young guys to build the instrument along the lines he had invented during the war to look for this radiation. We should just remind ourselves that it is radiation that fills space, that pretty unambiguously was produced when the universe was young. It has all the properties of thermal radiation, that it could only have acquired those properties when the universe was young and dense and hot. He said to me, go think about the theoretical considerations. That set my career. Some of the considerations I invented were reinventions, others were new. So yeah, I guess I can claim I did set the basis for this subject in many ways, but I certainly didn't start from scratch. No one ever does, let's face it. In particular, I was able to do this as a postdoc because the field of study of large-scale structure of the universe in the 1960s was so small. There had been great interest in this subject in the 30s, but by the 50s and 60s, interest had fallen away to the point that I, as a raw postdoc, had the field much to myself. I could do all of these interesting things. I wrote the book that he mentioned in the late 60s. I think it was published 71. Lots of stuff in there. It was wonderful. I could do it all by myself. No competition. It's so different now. Of course, I don't regret the old days because they're simply so much richer. But it was an amazing opportunity for me to do all of this interesting stuff without looking over my shoulder.
But then you, as was said yesterday, you laid a foundation that even if you didn't get everything right, it became the benchmark for the development of exercises to prove that there was physical evidence for what you were saying.
Yes, it's true.
And these were in a way to make our audience. I think you used the term fossils. This cosmic background radiation were like fossils.
Yes,
for
that's
the
right.
people in your field. Yeah.
Since the universe is not forever, it was different. It must have left evidence of that. And one fossil is this thermal radiation. I talked about lots of others in the book and about lots of puzzles. For example, it was clear even then that there's something wrong with our reckoning of mass. I mentioned Zwicky and his mass anomalies. I, in the book, collected many of these. In part, I was simply collecting bits and pieces of evidence that some people knew, but weren't realizing they ought to tell other people. Methods of analysis of large-scale structure, there were many things to be invented, so, well, what could I do? I invented them. Analysis of the degree to which the clustering exists and is evolving. The growth of mass clustering, of course, is key to our ideas about large-scale structure because we are forced into this notion that the galaxies are not forever. When the universe was young and dense and hot, there weren't any stars. They grew through the action mainly of gravity. And the analysis of how that would happen was certainly a large part of the book, and of course is now almost an industry.
Tell us a little about either one of these discoveries or this particular publication, what your feelings were as you came upon these ideas. You've just suggested that a lot of this had come before. You were putting it together.
Sure.
It was an uncrowded field, so we were in the phase of people didn't see the importance of this, so you didn't have to worry about what the competitors were doing at this moment in time and so on. I want a sense of the factors that made it possible for this to happen on the one hand. You mentioned some, and then what your feelings were as you were doing the work.
Do you know, it occurs to me that I was a little nervous. And you might ask yourself, why is no one else working on this subject? There was a very good reason. Although we had bits and pieces of evidence, they were rather scanty. This was not a subject at the time that was strongly supported by observational evidence. I do recall the feeling now that many of my colleagues and my superiors, the tenured faculty, although they never discouraged me from working on this subject, I got the feeling that they were saying, better you than me. How do you know you'll make progress in these great ideas? How do you know you'll be able to explore the universe at such immense distances and make sense of it and be able to piece it together into a well-established theory? I had no idea how far this subject would go when I was working on it in the 60s. In fact, to begin with, I think I remember correctly, I thought, well, I'll stick with this, write a couple of papers, and then I'll do something that makes some sense. It really was very speculative. How far could things go? In fact, I know for sure that I shied away from studies of the fossil thermal radiation during the 70s because as it was being measured, the measurements were very difficult, and the preliminary indications from those measurements was that this radiation didn't quite have the properties expected of it. So I went off and studied the distribution of galaxies. It wasn't obvious at all to me that this subject would have grown as rich as it now has. Who could tell? Technology advances.
So risk-taking, this is something that comes up with a lot of the scientists I interview, that you go out on an intellectual limb, I guess one would have to say.
How else are you going to do something new? And of course the limb can always break. Now,
you want
I must admit, I don't think I was at all being brave. Maybe I was being oblivious. But also, in those times, remember, this is not so long after the Second World War. Education was ramping up after the hiatus of the war. Faculty were being hired. Although it's true, I wasn't offered any other job than at Princeton. Somehow there was a feeling I could get a job if I needed it. That's not so much the case anymore. And it is a serious point of concern for a young scientist. Am I going to be able to continue my career? That's a real burden added on to all the other things you placed on the limb. I'm on the limb, I'm doing good work, but the limb breaks because I can't find a job. That is a real concern that didn't occupy me, and I think although I don't think I ever thought about it, it was for good reason. There were jobs. Yes, but no risk-taking.
And you mentioned in your lecture a postdoc whose name I don't remember, who committed early in his career to the development of the Cobe satellite, which became,
Yes.
Talk a little about that, because that was crucial for providing the evidence for some of these theories that we've been talking
Yes,
about.
I mentioned during the 70s the apparent evidence for anomalies that didn't make too much sense, that didn't make sense. It was obvious what to be done. Build a satellite devoted to the measurement above the atmosphere where the observing is much clearer. There was a young postdoc, a student of Paul Richards here at Berkeley, a graduate student, learned a lot from Paul, then moved to the East Coast. This is John Mather, and as a postdoc decided he would love to build the satellite that could do the job of studying this radiation above the atmosphere. As a postdoc, he recruited the help of some of the major people in the field, my dear colleague David Wilkinson, a few others. They got together, proposed to NASA to build a satellite. The proposal was accepted, and Mather, as a postdoc, stepped into the position of lead scientist at NASA to direct the building of this thing. It's a very difficult job. He has not only to understand the technology and the science, but also to hold off all of the bureaucrats who want, for example, to take away engineers working on his project and put them onto some other satellite. He has a marvelous book, The Very First Light, I think it's called, in which he details the agony as well as the ecstasy of building such a thing. Chapter after chapter of emergencies and who I turn to. 15 years of such work. He is now approaching middle life, and he has not a large record of academic accomplishments. It's all his eggs are in this one basket. He has the deep respect of a handful of people who know what's going on, but if that rocket had exploded on launch, and it happens, where's his career? A brave man.
Where do you see the most exciting problems down the road for this field, and what body of theories will be most instrumental in pointing the way, which would then have to be confirmed?
Yes. Of course, it's always controversial. Different people have very different opinions. Some will say cosmology is getting dull. We've answered the main questions. I don't understand why they say that. Well, perhaps I do. We have answered some big questions. Is dark energy really there? Yes. Is dark matter there? Yes. But what are these things? And so we have right in our face, up close, big open questions. Will we be able to answer them? Time only will tell. But of course, there are other directions to go, and they are not necessarily along the directions we've been following. For example, we think we're so smart. We understand galaxies. We don't understand our own galaxy. Astronomers are starting to turn back. See, there was somewhat of an imbalance in astronomy in the past decade or so, that the astronomy of the nearby universe was neglected in favor of the glamour of looking out to the edge of the universe. There is definitely fads. They operate in clothing styles and they operate in science. And the cosmology of the nearby universe, the science of the universe as studied by nearby objects, was neglected. In particular, our galaxy has been neglected. Shameful. We live here. We ought to look into it a little. It has lots of fascinating properties that will teach us about how it formed, or is teaching us about how it's formed. And these lessons are just being taught to us now. So very clearly, in the next 10 years, there's going to be a lot more work on nearby galaxies, studying in detail their properties and teasing out hints to how they formed which of course is what we attempt to understand when we look at distant galaxies seen in the past as they were forming. Clearly that's going to be a big activity. Finding nearby planetary systems, fascinating. Finding out if any of those planetary systems contain terrestrial planets, wow. Is there oxygen on any of them? How could you resist looking? Styles change because, in part, technology solves one set of problems, opens up others that maybe are so difficult that you will turn instead to areas you've neglected. And one thing about astronomy, you know, we're in no danger of running out of things to look at. It's a big universe.
And what about bodies of theory that might be brought to bear on these problems, some, you know, in other, you know, areas of the physical science?
Well, you know, I am particularly taken with the puzzle of the body of theory of the dark sector, so-called dark matter, dark energy. We pause to consider that in our sector, you and I, and the things we can see readily that interact with light, we have a set of laws of physics that are wonderfully simple. They're not all that simple, but they're pretty. You can write down the basic laws of physics on a couple of sheets of paper. Its expression is spectacularly complicated. As far as we know, you operate according to the laws of physics. At least you're to a good approximation to the known laws of physics. You are a spectacularly complex expression of a simple set of laws. In the dark sector, the laws of physics as we now postulate them are so amazingly simple that their expression is simple. They're dull. The dark matter piles up into what we call massive halos, the stuff that envelopes each galaxy. The dark energy just sits there, doesn't do much of anything at all. Is that really the way it is? Or is it the simplest, most ridiculously idealistic approximation we can get away with at our present level of knowledge? I emotionally reject that. It's strictly emotional. I say, I bet you there's a whole body of physics to be discovered that will describe the behavior of this dark sector. Call again in 25 years and see whether I was right.
I'm interested in that emotionally. So that is a, let's clarify that, it's a hunch based upon where you've been, what you've seen, what you've thought. Help me understand that.
Well, you know, let's face it. I'm asking myself, have I worked myself out of a job? Has the science of cosmology come to an end? It's in part, by emotional, I really meant, oh my goodness, fear. Put perhaps over-exaggerate. Emotion, yeah. I want the universe to be more complicated than it is, more interesting. That's an emotion, isn't it? It's a hope, a longing.
Yeah, it's a explanation of what drives that emotion.
Yes.
Yeah, and it makes sense.
I hope so.
Because isn't that key to what the enterprise?
Yeah, I hope so. I hope so.
Yeah. Okay, one final question, and that would be if students are really grabbed by, you know, the discussion of your career and of these set of problems, how would you urge them to prepare for their future in this field, build the groundwork, so to speak?
I have no idea. I have no idea. Work hard, do your homework, but keep interested in the world around you.
And it sounds like build things too in your particular field.
Yes, of course, each scientist is different. Some people build things a lot, others don't. Others have never touched a hammer. Now, there are no universal rules that I know of, aside from do your homework, but don't get locked up in your homework. I guess that's the real trick, isn't it? Because, you know, when we teach students in university, we set them exams in which the problems are totally artificial, because these are problems that have solutions. Nothing have known solutions. Nothing you do in research has a known solution. If it had a known solution, you wouldn't be doing it. So we teach these students the wrong thing. It often puzzles me, why are we doing it that way? Well, the only answer I know is we don't know a better one. But the real trick for a developing scientist, I believe, is not to get locked into being totally adept at answering already solved problems. Treat them as what they are meant to be, practice. Keep your mind ready to address the unknown.
On that note, Jim, I want to thank you for taking the time to have this conversation and share your intellectual odyssey with us. Thank you.
It's been a pleasure.
And thank you very much for joining us for this conversation with history.